Okay. And also I will record from this lecture, I will record all the lectures, and we'll share the link to you after the class. Okay. I mean, you can rewatch this video, or if you have anything missing during the class, then you can watch the video. Okay. Okay. So today, but you have to attend this class. Okay. Um, so today we will learn about machine learning basics. So in previous lecture, I introduced some graph showing that before the deep learning, the machine learning algorithms such as SVM was the best algorithm that performs the image classification, right? So during this lecture, we will learn about SVM and which kind of features are used for performing the image classification in like 2011 and 2010, okay? It's almost 15 years ago. This kind of method was state of the art. But after a few years, the algorithms are gradually replaced by the deep learning. So after learning this machine learning basics, we will learn the deep learning algorithms, and then we will learn how deep learning could be applicable to more complex computer vision applications. Okay. Before that, maybe you have to know, is there someone who already took machine learning class before? Please raise your hand if you already took machine learning course. So in CSC, there's a machine learning course, right? So is there anyone who already took that? No, nobody took machine learning class? Hmm? So you are parallelly, is there anyone who are parallelly uh, are taking the machine learning course this semester? Okay. So, remaining, you are not taking machine learning and not taking, not took and not taking machine learning. Okay. So almost over half of the students are not knowing the machine learning. So I will briefly introduce about what is machine learning. Okay. So machine learning is the algorithms that can learn machines. Okay. It's simple actually. Uh, okay. Uh, Anyways, there's some inconveniency due to the recording. Sorry about that. Given input, we record that as data. Um, we will normally record that as input. For the system F, this is the machine actually. This is you can think this as some mathematical functions, right? And this is also we record that as the machine. Okay, this F. Okay, this F. And the X is input to this system, okay? And the Y is the output of this system. So if we input X to F, then there will be Fx, right? There will be Fx, right? This is the output of the system F, right? And Y means the ground truth. Okay. Ground truth means in Korean is the 정답. Okay. So we are expecting the function f outputs the ground truth, but unfortunately, if we are not trained, we are making this function properly, then the initial function f will output some incorrect values, which is far from the ground truth, right? Okay. So the objective of the machine learning is to make this function f, the machine f, to output some value which is close to the ground truth. Okay. So, I mean, we are wanting to make this f x close to the ground truth y. Okay. This is happening during the machine learning. Okay. We have to learn machines to output something that we are expecting. Okay. That is the machine learning algorithm. Many x and y pairs, we will make a machine f to output to make it work as we desire. Okay, that's the machine learning things. And I mean, subsequently, later we will see how mathematically we can learn exactly the function f. We have to actually modify function f to make it output the output that we desire, right? So later we will see that how we can do. But in general, you have to understand what is machine learning here, okay? And then during learning process, the objective is to make the function f to output, uh, I mean, so given this, we are given many data. So there should be n number of data, right? So, the input x1 and their corresponding ground truth y1. And also there should be the second data, right? And third data. And we are having this n number of data. Okay? So n is large number, okay? And we are making function f to output y1 for the input x1, right? And we will make function f to output y2 for the input x2, okay? So that is happening during the learning process, okay? Learning phase. Or we call it as the train phase. So we train or learn the function f to make it as we desire, okay? That is the learning phase. After learning the f, what we will do is we will give this function f some new sample x star. Okay. So we are desiring, the function f to output the plausible output y star. Okay. It will output this for a new sample x star, right? And we desire this close to their corresponding ground truth y star, okay? So, we call this as the test phase, okay? So there are always two phases in the machine learning algorithm, okay? Training or learning phase, and also the test phase, okay? So during the learning phase, we make function f using many data, right? And during the test phase, we input, noble sample to the function f, which is already learned, okay? And then we are expecting that output is close to ground truth because the function f is already learned, okay? This is what machine learning is doing, okay? Are you guys understanding? Right? Okay. Uh, so there are multiple ways to achieve this kind of machine learning things. So in overall, we are there are multiple ways. Actually, we categorize the machine learning algorithms into three categories. The first one is supervised learning, and the second is unsupervised learning, okay? And the last one is the regression, okay? So you have to understand what is supervised learning and what is sorry. There are two types of machine learning algorithm. The first one is supervised learning, and the second is unsupervised learning. So you have to understand what is supervised and what is unsupervised, okay? So in the supervised learning, here you can see the function f maps x towards y, okay? So this is actually the same thing I already say to you, okay? So given input x, we given input x and y, n number of data, we learn the machine f. And for the new sample x star, we are expecting it output the one we are expecting, okay? Um, and when learning the machine f in supervised learning, we need X and Y pairs, which means we need ground truth Y, okay? If we are using ground truth Y during the learning phase or the training phase, we call that as the supervised learning, okay? In Korean, this supervised means 지도하다, okay? So it's some sense it is meaning teaching, okay? So we are explicitly using the ground truth and learn function f, okay? Teach the function f to map x to the y, okay? This is the supervised learning, okay? And this is actually, you have to understand these things. Function f is parameterized by the weight w, okay? I mean, maybe you already learned about this type of linear equation, right? So this is the input x, right? And this A and B, depending on this A and B, the same input x is mapped to different output y, right? So during the training phase or the learning phase, given many data, this number of n number of data, if we decide this A and B, which best explains this n number of data, then it's the learning pace, right? Okay. So during the learning phase, what happens is at the initial stage, we randomly initialize this A and B. Okay. So at initial stage, this function outputs some incorrect values, which is not desired, right? Because it is randomly initialized. But using this n number of data, we can gradually update this A and B. There's some mathematical formula for this. So you believe that there is a mathematical way to update this A and B using this n number of data. Okay, later we will learn about that. Okay. Anyways, at the initial stage, there's a parameter that determines the characteristic of this function f. And initially, it is randomly initialized. So their output is far from what we desire, okay? But later, by seeing many data, we will update this A and B, which is the parameter for this function f, okay? And then after training, this function f with updated parameters a and b, when we input new sample, I mean, using the updated a and b, we can get the, we can predict the output value, which is close to the ground truth, y star, okay? So this is what machine learning is doing, okay? And I mean, we normally call this A and B, this type of, how to say, updatable scalar values as the parameters. Okay. And we will normally call this as W, or sometimes we call that as sector. Okay. So anyways, the function f, anyways, we have to edit some values inside the function f, right? To make it output something we desire, right? And we actually update their parameters during the training phase, seeing many data. Okay, that's the learning phase. And here, this fourth law is showing, this is another way to state these things. Okay, so this, all the things I already explained is the thing happening during the training, but we can say that in different words like this. So we will find the parameter W that is able to minimize the loss function L. Okay, what is loss function is? So the loss function L is defined as the distance between. So are you guys understanding this? And maybe you can also understand this one. So I will, because we are actually recording it, I have to write it here. Sorry. Maybe next time I will bring my window tablet. Okay, sorry. But distance between f x1 x ice samples output, okay, with their ground truth. This is y, sorry. Okay, this is y. So this means d function means the distance between the system F's output and the ground truth y. Okay, so this is actually the definition of the loss function L. Okay, so I already explained that during the training phase, we will decide A and B that best explains this n number of data, right? That means actually the same thing as minimizing this loss function. Okay, this loss means the output of system F to each samples. Okay, they have to. We are actually finding their distance to the system's output and their ground truth. Okay, and by minimizing this distance, we can actually well explain each sample. Okay. Okay. So our aim during the training phase is actually minimizing this loss function. So we sum up here by, this is the sigma function that is summing over all the data. Okay. This is n I is iterate through from 1 to n, okay, because there are n number of data. Sorry. Okay. Okay, so I is equal to 1 to n. Okay, we will sum up all the distance between the system's output and their ground truth. Okay, and by minimizing this, we can get the function f that best explains n number of samples. Okay, and also, how to say, where's the mouse? Okay. Okay. And also normally we use this type of Euclidean distance when finding their distance. So when finding the distance between this output and their ground truth, we usually use the Euclidean distance. Okay. And there could be another distance metric. Okay. So we will also learn about some other metrics that calculate the distance between output and ground truth later. Okay. Anyways, this is the supervised learning. So given n number of data and their ground truth y, we find some parameter that actually determines the function f, okay, their characteristic that can minimize the loss function. Okay. That is the supervised learning. But unsupervised learning means the learning method which does not require the ground truth y. Okay, so sometimes you have to collect this type of x1 and their corresponding ground truth y1 for n number of data, and this takes some effort. Okay, and sometimes collecting this type of data takes a lot of effort or time. So even it is almost impossible to collect data, okay? Especially for the ground truth. Okay? So in that case, we can take this kind of unsupervised learning approach, okay? But this is not always possible. And supervised learning, their function f is more robust, okay, because they are explicitly using the ground truth y. But unsupervised learning, it can be anyways usable for even for the case where your ground truth is not secure. It's not easily secured. Okay. Okay. So where is the mouse? Okay. Now the function f here on supervised learning, still you will find some output y from the function f, but this is only for the testing phase. Okay, so the objective of testing phase is to find some output for a given input x. Okay. But during the training, when deciding the function f, you will not use any ground truth information y, okay? Does not use ground truth y when deciding function f. That is the unsupervised learning, okay? Usually, they only see the X input similarity or dissimilarity, okay? We call that as the geometry of X, okay? So we will see the example of this later, okay? Actually, there are two types of learning method in machine learning. And also, you have to remember these three tasks in machine learning. That is the clustering, classification, and regression. Okay. I will first explain about this classification. Okay. As the image class, you may remember the image classification, right? So this is the, representative computer vision tasks. Especially image classification, that is representative computer vision tasks, okay? And that is the, popular task in the supervised learning, okay? So in classification, for image classification, the X is input, and which is the image, okay? And the Y means the semantic class, okay? 혹시 에어컨 안 나오네? 왜 이렇게 더워? 온도가 몇 도예요, 지금? 26. 원래 안 내려가나요, 여기? 아, 알겠습니다. 다른 수업 덥지 않아요, 다들? 오케이. Don't know why. 이 강의실만 그런가? 어, 내려가. 오케이. Uh, yeah, this is the classification task. And another important supervised learning task is the regression. I mean, um, there is also ground input X and the ground truth Y in this regression task. So this is the supervised learning task, okay? But the thing is, the ground truth Y is continuous in this regression task. In the classification task, the Y is some integer value, maybe 0, 1, 2, 3, that represent the index of some semantic class. Okay, if it is 0, it means dog. If it is 1, it means cat. Okay, if it is 2, then it means some other semantic classes. So this is what we define the ground truth Y in the classification task. So the output Y is somehow discrete, okay? But in regression task, the ground truth Y is continuous, which means, for example, uh, let's assume that we are trying to regress height from the weight, okay, over person, okay? So, for example, when a person weighs 48 kilogram, then estimate his height, okay? This is a representative example for the regression task, okay? Their height is the continuous value, right? So any continuous height could be there, right? Okay, as the output, right? Are you guys understanding? Okay. Anyways, because there are X and Y is used during the training. So in that sense, this is the supervised learning task. But the clustering, this is the unsupervised learning task. Okay, so, and clustering is actually the representative task in the unsupervised learning. I will show you. It takes time, sorry. Maybe I have to show you this type of slide first. So in the clustering, there are many algorithms, and this k-means clustering is one of the popular clustering algorithms. So the left side, you are given some samples. Each green dot is meaning each sample, okay? And it has two-dimensional vector. The green dot, that is the two-dimensional vector. So which means here, this point, their X values are around 60, right? And their Y values are also around 60, okay? So, 60, 60, that represents that green dot, okay? And other green dots are also having two-dimensional values, right? Okay. And there are, I don't know, almost 20 or over 20 samples in this left graph, okay? And we want to somehow cluster this data, okay? And the right is the clustering result, okay? So which means, we have to specify how many clusters we want to do clustering. So here, we specify 2 clusters, okay? The right graph is showing the result, two cluster clustering result, okay? The blue dots and red dots, blue dots meaning the first cluster and the red dots meaning the second cluster, right? So, when you are given the left graph, humans, and also you are, asked to perform the clustering with 2 clusters, you will do it right, like the right one, maybe, right? Are you agree? Okay. Because their, values are somehow, in the dots, in the blue dots, their, values, the X values are similar, right, each other, okay? And the red dots, their values are also similar each other, right? And the one in red are far from the ones in blue, right? So because of that, when you are asked to perform the clustering with the 2 clusters, you will do that like the right one, right? And actually the clustering is doing this kind of thing. When performing this, we do not require any ground truth Y, okay? We do not prior know the dots in the red are from the second cluster and the blue dots are coming from the first cluster, but by seeing their geometry, by seeing their similarity and dissimilarity, we can cluster their, clusters, okay? We can perform the clustering on these samples, right? And this is the unsupervised learning task, okay? Are you guys understanding? Okay. And I will first explain about this k-means clustering algorithm. Okay. Uh, k-means, what k means here, what I mean, this k specify here means how many clusters you will have. Okay. So in this example below, there k is set as 3. Okay. So initially at initial stage, this k value is randomly initialized. Their k values are randomly initialized. Okay. So I will show you how computer algorithms are doing clustering, seeing their geometry. Okay. Seeing only their x input. Okay. This K1, K2, K3, those are randomly initialized centroid. Centroid means center of the samples for cluster, each cluster. And then what you will do right after doing the initialization is for every blue point here, you will calculate the Euclidean distance between all the samples, okay? So, you first map this sample to one of K1, K2, K3 by calculating their distance. In that case, you may assign this first sample into K1, right? Because it is nearby to the K1. And maybe for this sample, you will assign it into the K1 as well, right? But for this one, you will assign it to K2, right? By calculating their Euclidean distance, you will assign every point into one of three centroid, okay? And you can achieve this, right? So green point are assigned to the first cluster because it is, K1 was the nearest point to them, okay? And red point are assigned to the second cluster because K2 was the nearest point, right? And same for the K3, right? First assign every point in the space into one of the centroid. That happens first. And then what happens next is you will update K1, K2, K3. How you can calculate you can usually calculate the average of green samples, right? So you can update K1 by calculating the mean of green samples, right? And also you can update K2 by calculating the mean of red samples, right? And then you can update K3 by averaging blue point, okay? That is actually new centroid. And then you iterate this, and you again assign all the samples to one of K1, K2, K3 by calculating the Euclidean distance to them. Then previously, for example, this sample was green, right? Previously, for K1, which is randomly initialized, this one, the leftmost one, this one was green sample, but now it becomes to the red, okay? Anyways, if you do that iteratively, then you can find, you can find the true centroid and their true clusters, okay? That is the K-means clustering algorithm, okay? Are you understanding? Okay. So, this iteration could be done for maximum iteration number you specify. For example, if you want to do this iteration for 100 times, you can specify 100 for loop, right? And or if K1, K2, K3 is not changed much, you can also stop the iteration, right? So that is the two popular termination condition when terminate this for terminating this k-means clustering. Okay, are you guys following this? Okay, and this is somewhat complex, but this is actually explaining what I explained already. So you have to specify k, right? Large K, which means the number of clusters, right? And you have to have xi, which is the n number of samples, right? And also you need distance metric to calculate the similarity or dissimilarity between samples and centroid, right? This is the input. And output means, where is the output? Output means the clusters Y for n samples, right? Okay. And you will initialize K cluster centroid, which is the previously it was K, okay? The notation was small k, but this is changed to Ci here. And there should be K number of centroid, large K number of centroid, okay? This is randomly initialized if there's no prior knowledge, okay? In most of case, this is randomly initialized, okay? And you will repeat these two steps until the termination condition met. Okay. So you will assign all the samples to one of the nearest centroid. Okay. You can mathematically formulate that like this. Okay. So arg mean means you will get the k that whose distance between centroid and that samples is minimized, and this is the output y for i's sample xi, and you will get their cluster by finding the nearest centroid. Okay, that is meant by this formula. Okay, and then the second phase, you will update the centroid. Okay, you will update the centroid. Delta means delta function means uh, I mean, if the statement inside this parenthesis is true, then this delta function is 1. Otherwise, this delta function goes to 0. Okay, that is what delta function means. So, actually, this part means the number of samples in that cluster. Okay, and the above thing means, the sum of their xi values. So this is actually meaning averaging all the samples inside the cluster. Okay. If you follow this formula, this is high school mathematics, right? So, this is actually finding the average for the sample xi, which is in the cluster, in each cluster, right? So this slide is meaning explaining what I explained using the figures, right? Okay. So this is the k-means clustering, and you can actually implement the things using the code like this. So this is the thing for maybe importing some packages, okay? And this is the thing for generating the green dots, okay? So, this random int is randomly generating some integer values, which is inside this range. And they are generating 25 samples who has the 2 dimension. Okay? And their values is having this range from 25 to 50. Okay. And for Y sample, this is the samples for X, and this is for samples, sorry, samples for Y. Okay. This is samples for Y. So you are making actually 50 overall 50 samples. Okay. Okay. And here, this CV2.k-means, this is actually a k-means algorithm implemented in the OpenCV library. So this function is actually doing the k-means clustering. Okay, the algorithm is quite simple, so maybe you can by yourself implement this k-means algorithm, but using the OpenCV, you can easily perform the k-means with the one line of code. Okay, so this G means the feature vectors, which is the input. Okay, and this 2 means the dimension of the feature, and this 10 means the iteration number, and this flag is meaning how you will initialize the centers. Okay, and this criteria means the termination criteria, and it is actually defined here, right? And this criteria EPS means EPS and also criteria max iteration. Those two are specifying the one I mentioned to you. So if the overall iteration reaches the maximum iteration number you specify, or or is meant by this plus sign. If because you are specifying this as plus, that is meaning or. So either maximum iteration number is reached, or there's no significant change. That means by this EPS. And this 1.0 is actually means the I mean EPS value threshold for the EPS. I mean the change of pixels are less than 1 pixel, then it will terminate. And also this means when your iteration is over 10, then it will also terminate. So that is meaning the criteria here. Okay. And also this A and B means the cluster, actual the cluster output, okay? And this is for code for visualizing everything, okay? So you can run this code to practice this k-means clustering, okay? So we learned these basic machine learning things. There are supervised learning and unsupervised learning, and we already learned k-means clustering. And there are classification and regression. So we will learn how to implement this regression and classification during this course. Okay, don't worry. Okay. And also, I already told you there are object detection task, and image segmentation task. Okay. Those are also mostly done by framing as supervised learning. So X, the input is image, and Y is some of the bounding box location and also the class inside the bounding box for the object detection task. And for the segmentation task, the X is each image pixel and Y is the class for image pixels. Okay, so this is also the supervised learning task. And this graph is also showing the thing I mentioned previously. So in 2010 and 2011, I already mentioned that these are implemented by the shallow learning algorithm. Okay. And I also mentioned that these are done by SVM. So we will, during this lecture too, we will learn about these early algorithms right before the deep learning, okay? And after that, we will learn about deep learning algorithm and also review AlexNet, BridgeNet, GoogleNet, ResNet, okay? We will see their detailed architectures, okay? And this bag of words model, you have to maybe nowadays we are not anymore using this bag of words model. I mean, this is quite traditional approach to, I mean, achieve the image classification before deep learning. Okay, in early 2010s, we are using this bag of words model for describing each image. And then we classify this BOW representation using SVM. Okay, that was the state-of-the-art algorithm, actually written the leftmost part. Okay, I will explain you. And during this, I mean, this pipeline, they are having both clustering and also the classification. So I think this is the good example, good exercise for understanding what is clustering and what is classification. Okay, and also you assignment 1 is implementing this. Okay, so I mean, there are already code inside the materials. So, I mean, if you are carefully following everything in the material, then the assignment 1 will not be too difficult. Okay. The bag of words means uh, is meaning like this. So, sorry. I mean, it was originally used to encode the text signals. Okay, so I mean, for the text, for example, the newspaper, there are some important words, and also there are also unimportant words in the paragraph, right? So I mean, the example of important words are this type of sensory, brain, visual perception, that is meaning some semantic things, right? But unimportant words are like of, are, this type of words are also important to understand details, but it's not directly related to the topics of the paragraph, right? So bag of words, this is the representation that roughly capture the topics of the text. Okay. So actually they want to make some histogram of the words for encoding the text paragraph. Okay. If you encode all the paragraph as the histogram of the words, then that representation is somehow encode the topics, the semantics of the paragraph, right? Right. So, I mean, this is showing somehow that kind of thing. So left is having that kind of keyword, right is having those kind of keyword. If you make histogram for this different paragraph, then their histogram looks quite different. Okay, this difference, Euclidean distance between the histogram level will be far, right? Okay. I mean, yeah, this is the idea of bag of words. Okay, when encoding text, somehow you want to pick some important words into the bag, and this is meaning actually histogram. Okay, bag of words means histogram of words. Okay, but conceptually it is I mean meaning taking some important words in the bag. So that's why we call that as bag of words. Okay. In the text domain, this is quite simple. I mean, because the words are already well defined in our language. Okay. But the thing is, when trying to encoding this type of images as the histogram of some words, in image domain, there is no such predefined words. Okay, that was the problem in the image domain. In the image domain, they also want to encode the images as the bag of some visual words. But the problem is there's no predefined visual words. Okay, like the language, there's no words. Okay. What they do is, in this bag of words pipeline, they first extract this type of features. Okay, at that time, there's already some many methods that can extract some useful features from the images. For example, color information is one of the, how to say, easily extractable features from the images. So each pixel is having RGB value, and that color is actually, how to say, most naive features we can extract from the images. Also, if you extract some gradient, I don't want to deeply explain about this, but images are somehow array Okay, and you can get some 2D gradient. You can calculate some 2D gradient, and that gradient is meaning some of the directional information in the images. Okay, so for example, if you extract some gradient for this type of images, this type of directional information, considering their pixel values, their edges, we can somehow extract some of the shape and appearance information by calculating their gradient. So that gradient is one of the popular feature representation during this time, but no more used nowadays. Okay. Anyways, from all the training images, we first extract the features, which is actually the vector. How to say? So mathematically, it is a vector. So normally we use 256 dimensional vector. We extract those dimensional vector from all the patches of the images. Okay. So for this part, you can just accept. Okay. So I don't want to go deep into this because there are many things we have to learn, and this is not used anymore. So there are some pre-existing techniques that can extract some useful feature vectors such as shape, appearance, color information from the images. Okay, there's already, and in OpenCV that is already implemented as well. Okay, so from the training images, we extract feature vector for all the patches in the training images. And this is somehow conceptually drawing that feature vector. Okay, that patches is meaning such feature vector. And after that, what we do is we apply the clustering algorithm on that extracted feature vectors. Okay. Especially, we are normally using k-means clustering algorithm on the extracted feature vectors. Okay. For example, if we specify k as 1000, then extracting all the feature vectors from the images, training images, and then we can cluster those features to form 1000 visual words. Are you guys understanding? Then somehow, by clustering all the features extracted from the training image, we can somehow generate the visual world looks like this. Are you guys understanding? Okay. And then for the new image patches, we will calculate the distance between that patch and 1000 visual words, and then assign that patch into one of the visual words. Okay, and that can generate this type of histogram, right? Okay. Okay, so we first extract from the training images, we extract features and then cluster to make this type of visual dictionary. And then using that visual dictionary, we represent images as the histogram of these visual words. Okay. Understanding this, right? And then we will apply machine learning algorithms such as SVM to discriminate the histograms, which means map the histograms into one of the semantic classes. Okay, that is actually the bag of words pipeline. Okay, so we want to encode images as the histogram of the visual words. Okay, for doing that, we apply clustering algorithm on the image patches to make the visual words. Okay. So this is, summarizing all the things. So there's already pre-existing way to extract useful patches from the images. And then there's already method that can describe, that can, calculate some useful information and extract some n-dimensional vector from those patches. Okay, there's some feature extraction pipeline already. And from all the training images, we achieve that, extract all the features from all the training images. And then we will apply uh, clustering algorithm by mapping those features into their feature space. By applying k-means clustering, we can get k number of visual words. Their centroid becomes the visual words. Okay. Okay. And this is examples of the visual dictionary. Okay. I mean, okay. Okay. This is the clustering we already learned. Okay. And then after making this type of visual words, what we will do for the testing image is using the training images, we construct the visual words, right? And for the new input X star, that is image, we will also extract some useful region, useful patches, and we will encode that as some vector, right? And then this is already learned visual words, and we will map each patches in the testing image we will map them into one of the visual words by calculating their distance. Okay. And by doing this, we can represent testing images as the histogram. Okay, right? So now we can represent images as histograms of the visual words. Okay. And then this is again, again summary of backward-forward pipeline. But I mean, this is the first part. This is the first part. So the thing I have explained is the first part. So from the training images, I extract a lot of features, and then by applying clustering algorithm, I made visual dictionary, and then I represent each image as the histogram of visual words. Okay, and then we will also represent all the training images as the histogram of the visual words. Okay, and then using that, we will train the SVM as the image classifier. Okay, this is a new part. Okay, previously I mentioned that we can encode images as the histogram of visual words. Okay, and using that histograms, we can train machine learning classifier such as SVM to map that histogram towards semantic classes. Okay. This is the training stage. So training stage, using the training images, we construct visual dictionary and train the machine learning classifier such as SVM. Okay. And then for the new testing image, we extract the features again and map it to find the histogram of visual words by mapping each local patches, their features into one of the visual words, okay? And then using the machine learning classifier, we can classify that histogram representation into semantic class, okay? Are you guys following this? Okay. This is backward-forward pipeline for achieving image classification in early 2010s. Okay. So and maybe next Wednesday we will learn about what is SVM. Okay, so we learned about backward first and the clustering algorithm, and then we will learn now SVM. Okay, and here this part I wrote all the code for implementing this BOW things. Okay, so I mean you can try. Okay. But using OpenCV, I mean, everything becomes very easy. So this is only having few lines of code, right? Okay. So yeah. So next class, we will learn about SVM. Okay. Thank you and see you this Wednesday.